Hello everyone, today I'm presenting a paper on REDQUEEN, fuzzing with input to state correspondence. It was published at NDSS in 2019 by researchers at Universität Bochum in Germany. By the end of this presentation, you should have a solid understanding of what fuzzing is, what specific problems REDQUEEN was trying to solve, and the clever, almost surprising, simple idea they came up with to solve those problems. Also share some results and flag some weakness in the paper. So let's get into it. Before we can appreciate what REDQUEEN does, we need to understand fuzzing. The core idea of fuzzing is this. Take a program, throw a huge amount of weird, malformed, or random inputs at it automatically, and see if any of those inputs cause it to crash. Crashes can reveal security vulnerabilities, buffer overflows, use after free bugs, and so on. There are three flavors of fuzzing. Black box fuzzing treats the program like a complete mystery. You just mutate inputs randomly without any knowledge of what's happening inside. White box fuzzing goes to the other extreme. You use full program analysis like symbolic execution to reason about the program mathematically, and then there's gray box fuzzing, which sits in the middle. You instrument the program to collect lightweight feedback, specifically code coverage, and use that to guide what mutation to try next. The key question is to ask yourself is, if you were trying to find bugs in, let's say, a PDF reader, without having access to the source code, how would you do it? So REDQUEEN built directly on top of a tool called AFL, American Fuzzy Loop. So let me give you a quick history lesson. Before AFL, fuzzing was mostly black box, random mutations with limited coverage. Around 2013 and 2014, AFL came along and changed everything. It uses lightweight, compile time instrumentation to track which edges in the program's control flow graph and input exercises. If a mutated input exercises a new edge, AFL saves it to the queue and keeps fuzzing from there. Everything else gets thrown away. In 2016, DARPA ran the Cyber Grand Challenge, a fully automated cyber reasoning competition, and every single team used fuzzing as their primary bug finding technique. That's how important it had become. And after CGC, there was an explosion of AFL-based tools, AFL Fast, LAF Intel, Angora, and TFuzz, and more. Each one tried to make AFL smarter in some way. REDQUEEN published in 2019 one of these tools, and its contribution is really elegant solution to a specific class of problems that has been blocking fuzzing for years. So what are those problems? They're called fuzzing roadblocks, and the two biggest ones are magic bytes and checksums. Look at the code on this slide. The first check says only proceed if the first 8 bytes of input are exactly the string MAGICHDR. If you're randomly flipping bytes, the probability of accidentally guessing all 8 bytes correctly is essentially 0. So the fuzzer never gets past this check. Coverage stalls. The fuzzer is stuck. The second example is even worse. There are 2 nested checksum checks. The input had to contain a checksum over part of itself, and then a magic 2-byte sequence. If the fuzzer somehow mutates the input to get past the first check, the mutation will almost certainly break the checksum, and the second check fails anyway. It's a dead end. These aren't toy examples either. Real-world light formats like PNG, zip, and network protocols use magic bytes and checksums everywhere. Without solving these roadblocks, a fuzzer can't meaningfully test a huge chunk of real-world software. So before REDQUEEN, these were 3 main approaches. There were 3 main approaches to dealing with these roadblocks. The first is taint trafficking. You label every byte of input with a tag and then track how those tags flow through the program. Those operation, assignments, comparisons. When you hit a comparison, you know exactly which input byte you need to change to pass it. The problem is that taint tracking requires a very precise model of the environment. Library calls, OS behavior, instruction semantics. It falls apart on complex instructions like floating point or on closed source programs where you don't have that model. The second approach is symbolic execution. Instead of running the program with concrete values, you treat the input as symbolic variables and you build a path constraints as logical formulas. Then you ask an SMT solver to find inputs that satisfy those constraints. It's powerful, but it suffers from path explosion. The number of possible paths through even a small program grows exponentially, and it's very slow on real-world binaries. The third approach is program transformation. It's called tools like tfuzz. You patch out the hard check, fuzz the modified program freely to find interesting paths, and then use symbolic execution at the end to fix the broken inputs. It works, but it introduces false positives, and you end up spinning up a new fuzzing instance for every hard-to-reach piece of code. It doesn't scale well. All of these approaches are the opposite of ALF's philosophy. Make new assumptions, stay fast, be robust. REDQUEEN asks, is there a simple way? And here's the answer. This is the central insight of the entire paper, and honestly, once you hear it, it feels almost obvious. In many programs, parts of the input ends up directly in the program state. If the program reads 8 bytes from the input and compares them to a magic header, those 8 bytes show up almost unchanged in the register at the time of comparison. There's a direct observable correspondence between what you put in the input and what you see at runtime. So instead of doing expensive taint tracking or simple execution, REDQUEEN just watches. It runs the program once with the current input, hooks every comparison instruction, and records both sides for each comparison. Then it asks, does one of those sides look like something from my input? If so, I know what to replace it with. Look at the diagram. Input, test, seed, input. Input is test, seed, input. At the comparison instruction, it sees D as test on the left. That's just test seed interpreted as a little Eden 64-bit integer, and RDHC IGAM on the right, which is MAGICHDR in Little Eden. And REDQUEEN observes this, reverses the encoding, and generates a mutation. Replace test seed in the input with MAGICHDR, new test case, MAGICHDR input. It passes the check. No taint tracking, no SMT solver, just observation and substitution. So let me walk you through exactly how the magic byte technique works in practice. Step 1 is tracing. When REDQUEEN picks up a new input from the queue, before it starts fuzzing, it does one single trace run. During this run, it hooks every compare instructions, every subtraction, since compilers sometimes use those instead of direct comparison, and every function call that might be a string comparison. It records both arguments. Step 2 is colorization. This is a clever trick. The problem is that if your input is full of 0 bytes, a comparison with any 0 values could match at thousands of positions. So REDQUEEN first tries to replace as many input bytes as possible with random values without changing the execution path. This dramatically reduces the number of places where a pattern could be found, usually by orders of magnitude. Step 3 is generating mutations. For each comparison observed, REDQUEEN creates a mutation. replace the left-hand pattern found in the input with the right-hand comparison target. It also tries +1 and -1 variants, which helpfully catches off by 1 bugs as a side effect. And it tries multiple encoding, little Eden, big Eden, 0 extended, as a C string as ASCII digits to handle the common ways programs decode input before comparing it. The whole trace runs just once per input. All the actual fuzzing runs without any overhead from this analysis. So checksums are trickier because you can't just substitute a value. The checksum is computed over the rest of the input, so changing any byte breaks it. REDQUEEN's approach has 3 phases. First, identification. During the colorization step from before, REDQUEEN notices if the right-hand side of a comparison changes when a random bytes are injected. And if it does, that suggests it's a computed hash over input data, not a value that comes directly from the input. REDQUEEN flags that instructions as a suspected checksum check. Second, patching. REDQUEEN replaces the flagged comparison with one that always returns true. Essentially, it punches a hole through the checksum. Then it fuzzes the modified binary freely. Now the fuzzer can explore all the code that was previously locked behind the checksum. Third, validation. When the fuzzer on the patched binary finds an interesting new path, REDQUEEN enters a repair phase. It uses the same input-to-state technique from before to figure out what the correct checksum value should be for this particular input, and fixes the checksum field. Then it runs the repaired input against the original unpatched binary to confirm it actually works, and if it does, great. It goes into the real queue. If it doesn't, the patch is removed. This ensures that every single input in REDQUEEN's queue is a valid, real input that works on real binary. 0 false positive. And it handles nested checksums too, by building a dependency graph and fixing them in the right order. Quickly on the implementation, REDQUEEN is built on top of AFL, which is an AFL-inspired fuzzer that uses Intel processor trace for coverage feedback. Intel PT is a hardware feature that records the control flow of the CPU at the hardware level, with no instrumentation needed in the target program. This means REDQUEEN can fuzz closed source binaries, kernel code, 32-bit and 64-bit targets, anything you can run on an x86 processor. The target runs inside a virtual machine managed by KVM and QEMU. REDQUEEN uses VM introspection. Basically, it can pause the VM, inspect registers and memory, insert the breakpoints and patch instructions, all from outside the VM. This is how it works comparison instructions and patches checksums without touching the target binary on disk. The critical design decision is that analysis phase. The tracing, colorization, and mutation generation runs only once per new input added to the queue, and all subsequent fuzzing happens at full speed with 0 overhead from the analysis. So now let's look at how REDQUEEN actually performs. The most commonly used benchmark for fuzzing research is called LavaTech-M. It takes real programs from GNU Core Utils suite and artificially injects known bugs at hard-to-reach location. It then becomes a competition. How many of the 2,265 planted bugs can the fuzzer find? REDQUEEN found over 114% of the listed bugs, meaning it found them all plus additional 337 bugs that the Lava and Arthur hadn't even listed, bugs they thought were unreachable. And REDQUEEN found them all within 25 minutes, while other tools would take over 5 hours. For comparison, Angora, which uses proper train tracking, found about 1,443 bugs in the hardest program called Who. REDQUEEN found 2,134, nearly 50% more, and found 3 times as many unlisted bugs. The gap between REDQUEEN and everything else on this benchmark is pretty striking. It's worth asking whether Lava M is genuinely representative of real-world bugs, and the author's acknowledges it essentially entire. And the author's knowledge isn't entirely, but the numbers are hard to dismiss. More convincingly, REDQUEEN was run against real-world, heavily tested software, programs that had already been fuzzed by other tools, and it still found new bugs. In total, 65 new bugs across 18 different programs and OS kernel drivers and 16 CVEs. This includes object dump, AS and NM4, binutil, libtif, ImageMagick, Wine, Bash, Perl, mruby, libxml2, and kernel-level file system drivers hfs.ko and nfts.ko. There are a couple of highlights worth mentioning. In mruby, REDQUEEN found an integer overflow in a string resizing function. The overflow was actually silently removed by the compiler's optimizer, and the compiler saw that a signed integer can't technically overflow in standard C, so it removed a safety check. The bug only existed in the compiled binary, not in the source code, and source level analysis would have completely missed it. REDQUEEN found it because it works on the actual binary. In object dump, REDQUEEN auto-extracted a section name from a hash table lookup function, a case that basically no other fuzzer handles, and automatically used it in the right position to explore new code. This raises a good question. Why does binary-only fuzzing matter? Think about proprietary software, embedded firmware, OS kernels. You often don't have source code. REDQUEEN works there too. A concern you might have is, doesn't all this tracing and colorization make the fuzzer slow? The answer is no. And the design is deliberate. Because the analysis only runs once per input in the queue, and the queue is typically a few thousand inputs, while fuzzing runs millions of times, the analysis cost is completely amortized. On the binutil benchmarks, REDQUEEN and plain KAFL ran at about the same number of executions per second. Even more interesting, the input-to-state mutation operator is by far the most efficient of all REDQUEEN's mutation strategies. On the binutil targets, it produced around 50 new coverage, triggering input per minute of time spent. The next best was the havoc stage at about 13 per minute. Deterministic stages around 5, and the Radasma stage was basically 0. So not only does the technique solve roadblocks, it genuinely the most productive mutation strategy in the entire fuzzer, even on input where there are no obvious roadblocks. No, and this is important, REDQUEEN is not magic. There are real cases where it doesn't work. The technique relies on input bytes bytes reaching the program state mostly intact. Whenever that assumption breaks down, REDQueen is blind. Three main cases. First, compression. The PNG format stores pixel data as zlib, compressed data. After decompressing, the data looks completely different from the input byte. Any constraints that appear after the decompression step are invisible to REDQueen. Second, hash maps. If a string from the input is hashed and used as a lookup key, REDQueen can't connect the output of the hash back to the input bytes. It sees a comparison involving a hash output and has no idea which input bytes to change. Third, novel encoding. Base 64 is a good example. REDQueen has a fixed set of encoding schemes it knows about. If a program uses something outside that set, REDQueen won't handle it. Though the authors note the encoding list can be extended. On the evolution side, there are also some legitimate concerns. The Lava M benchmark uses artificial bugs designed to test exactly this kind of technique. The comparison across tools use different hardware and time limits. And statistically, confidence from 5 runs is debatable. The authors are upfront about most of this, and they suggest REDQueen should be used as a first pass tool and combined with heavier analysis for cases it can't handle. So let's wrap it up. What should you take away from this paper? The key insight is simple but powerful. Programs often move input bytes directly into their state with minimal transformation. By observing comparison at runtime, you can learn what to substitute without any expensive formal analysis. It's a lightweight approximation to taint tracking and symbolic execution, and in practice it's faster and more widely applicable than either. The impact is real. REDQueen works on closed source barriers, kernel code, any platform that runs on x86 with no source code, no environmental model, no platform specific code. And it found 65 bugs in heavily tested real world software. The philosophy is pure. AFL. Make few assumptions, be fast, be robust. Even when REDQueen can't solve a constraint because data is compressed or hashed, it simply moves on. It doesn't break, it degrades gracefully. The paper is definitely worth reading for the full evaluation detail and the algorithm for nested checksums repair. And that's genuinely interesting. The code is also open source and the GitLab. It's also open source on GitHub, so if you want to try it out. And here are some questions to consider. Defensive implications, beaten the fuzzer, hybrid pipelines, coverage as proxy. So with defensive implications, if attackers can use this on closed source binaries at scale, how should defenders respond? Does this change how you design a protocol or file system? And for beating the fuzzer, could a program be designed to resist I2S, like for example by obfuscating magic values or using non-trivial encodings that actually improve security? And for hybrid pipelines, the authors suggest IS2 first, symbolic execution for hard leftovers, and what would a practical implementation look like, and when do you know to give up? And for coverage as proxy, the paper uses code coverage to measure bug findings. Is that valid? Can you have 100% coverage and still miss critical bugs? And what's the better metric? So that's the end of my presentation, and I hope you learned something. Yeah, bye.